Right now, a clock on the International Space Station is ticking 38 microseconds faster per day than the one in your pocket, and without measuring that invisible gap, every GPS on Earth would drift by 11 kilometers by tomorrow morning. By the end of this video, you will understand exactly how scientists reach into the unseeable, and you will never look at light, sound, or empty space the same way again. A single hydrogen atom is 0.0000000000106 meters wide, too small for any microscope to photograph directly, yet scientists know its diameter to 11 decimal places. The strangest part is this: almost every measurement of the invisible does not look at the thing itself, it looks at what that thing does to something else. Take light, the oldest measuring tool in science, because every element in the universe absorbs and emits light at a completely unique set of colors, like a fingerprint no two substances share. When you pass starlight through a prism and spread it into a rainbow, dark lines appear at precise positions. Those gaps are atoms in the star's atmosphere swallowing exactly the colors they are made of. In 1814, Joseph von Fraunhofer counted 574 of those dark lines in sunlight and realized he was reading a chemical recipe: hydrogen, sodium, iron, written in gaps of color across 150 million kilometers of empty space. Today, that same technique, spectroscopy, tells us the temperature, pressure, magnetic field strength, and chemical composition of a star 400 light-years away, from a single beam of its light. But here is the question that puzzled scientists for decades: how do you measure something that does not interact with light at all? Neutrinos are the answer to that nightmare, a particle so reluctant to interact with anything that 65 billion of them pass through every square centimeter of your body every single second without touching a single atom. To catch even one neutrino interaction, scientists buried a cubic kilometer of Antarctic ice under the South Pole and filled it with 5,160 basketball-sized light sensors watching for a single flash of blue light. That blue flash, Cherenkov radiation, is produced when a neutrino finally strikes a water molecule and the resulting particle briefly outruns light inside the ice, creating a tiny sonic boom made of photons. Think about that. Scientists measure an invisible particle by waiting for it to break the speed of light inside frozen water and then catching the glow, like timing the invisible by the ripple it leaves behind. But neutrinos are not even the most dramatic example, because in 2015, scientists measured a ripple in the fabric of space itself so small that it shrank the entire distance between Earth and the nearest star by less than the width of a proton. That measurement, a gravitational wave from two black holes colliding 1.3 billion light-years away, required building the most precise ruler in human history, twin tunnels each 4 kilometers long with laser beams bouncing inside them. Here is where it gets genuinely strange. The laser in LIGO is so sensitive that if an ant sneezed 100 kilometers away, the vibration would ruin the measurement, so they suspend the mirrors on glass fibers thinner than a human hair to isolate them from the Earth itself. This is the secret at the heart of invisible measurement. You cannot make the signal bigger, so you must make everything else quieter, hunt the signal by silencing the world around it. Temperature works the same way. Every object above absolute zero radiates infrared light, and the hotter the object, the shorter the peak wavelength, following a relationship so precise that scientists can measure the surface temperature of a star to within a few degrees just from the color of its glow. Wien's displacement law, derived in 1893, is why astronomers know that Betelgeuse glows red because its surface is only about 3,500 degrees Celsius, while a blue star like Rigel scorches at 12,000 degrees, all measured without a single thermometer leaving Earth. Now we are about halfway through this story, and here is the question worth sitting with: is there anything so invisible that even these extraordinary tools cannot reach it? The answer is yes. Dark matter makes up 27% of the universe, exerts clear gravitational pull on everything around it, and after a century of searching, scientists have never detected a single particle directly. Yet scientists measure dark matter's shape and mass every day, not by seeing it, but by watching how its gravity bends the light from galaxies behind it, warping those distant galaxies into arcs and rings the way a wine glass distorts what you see through it. By mapping where those arcs appear and how distorted they are, scientists can reconstruct a precise three-dimensional map of invisible dark matter, like drawing the shape of an underwater rock by watching how waves bend around it on the surface. This method, weak gravitational lensing, mapped the largest structures in the universe across 2 billion light-years in the dark energy survey, and every data point came from a distortion tinier than the thickness of a human hair relative to the full image. But the most personal and visible thing science has ever measured is something inside you, the electrical signal firing across your neurons right now as you process these words, traveling at up to 120 meters per second along fibers thinner than a spider's silk. An electroencephalogram, EEG, measures that invisible electrical storm through the skull without touching the brain, detecting voltage changes as tiny as 1/1,000,000th of a volt, a signal roughly 1 billion times weaker than a phone call. The trick is not to amplify the brain signal, that just amplifies the noise, but to repeat the measurement thousands of times and average everything together, because random noise cancels itself out while a real signal keeps returning in the same place. That same averaging trick, called signal averaging or stacking, is how astronomers pull the faint radio whisper of a galaxy 5 billion light-years away out of a sky full of interference from passing satellites, microwave ovens, and even cosmic background radiation left over from the Big Bang. Here is the second biggest revelation of this whole video, the cosmic microwave background, the afterglow of the Big Bang, 13.8 billion years old, was first detected because two scientists at Bell Labs thought the persistent hiss in their antenna was pigeon droppings, and spent months cleaning the dish before realizing the noise was the birth cry of the universe. Penzias and Wilson's accidental measurement in 1965 gave us a snapshot of the universe 380,000 years after the Big Bang, and tiny temperature variations in that ancient light, just 0.00001 degrees, are the seeds from which every galaxy, star, and planet you have ever seen eventually grew. So the invisible is not one category, it is atoms too small, wavelengths our eyes skip, fields that pass through matter, particles that hate interaction, ripples in geometry itself, and signals buried under noise, and every single one has yielded to a different ingenious trick. The pattern behind every invisible measurement is the same: find something the target thing reliably changes, and measure that change with ruthless precision, the shadow, the ripple, the bend, the glow, the gap in the rainbow. Atomic clocks do this with a cesium atom that vibrates exactly 9,192,631,770 times per second, a frequency so stable that if you ran two atomic clocks for 300 million years, they would disagree by less than 1 second. That precision is why scientists could confirm Einstein's prediction that time runs faster when gravity is weaker, measuring not philosophy, not abstraction, but the actual, literal, ticking difference in two clocks placed on different floors of the same building. The measurement of the invisible has a strange consequence that scientists rarely discuss out loud. Every time we built a new instrument sensitive enough to see the next layer of reality, we discovered that reality was stranger than the instrument we built to find it. Planck's constant, the tiny number that governs quantum mechanics, was discovered because blackbody radiation just would not fit any classical equation, and the fix Planck himself called an act of desperation, turned out to describe the deepest rules of matter. Every one of those discoveries lived inside data that had existed for years. The answer was always there, invisible in plain sight, waiting for someone to ask a slightly different question of the same numbers. Here is what that means for you, the person watching this. The universe is not hiding anything from you out of cruelty. It is hiding everything from you because the universe communicates in signals your body was not built to receive, and science is the translation layer humans built to hear it anyway. Every measurement of the invisible is ultimately a record that a human being refused to accept that something real could not be known, and they were right, every single time. The atoms in your body were measured spectroscopically in stars that lived and died before the sun existed, meaning the tools to read the invisible did not just expand our knowledge of the universe, they revealed where you literally came from. In the end, to measure the invisible is to insist that the universe owes us an answer, and the most humbling discovery of all is that it does, every time, if you are patient enough and quiet enough to hear it. Follow Science Explained daily for more.